Viscosity is the resistance of a fluid to sliding motion under a shear stress. Consider the shown large flat plate that is being pulled on the surface of the shown fluid at a constant velocity, which we denote as capital U. It is separated from a large parallel flat wall at the bottom of the fluid container by a small distance, capital Y. The surface area of the plate that is in contact with the fluid is denoted by capital A. Since the vector for this area is pointing in the negative y direction, we call this area capital AY. In order to maintain this constant velocity against the viscous forces that tend to slow the plate down, a force F in the x direction must be applied continuously. Hence at steady state, the applied force Fx is balanced by an equal and opposite force due to the liquid's viscosity. According to the no-slip boundary condition, the velocity of a fluid layer that is in contact with a solid wall is equal to the velocity of that solid wall. Therefore, the velocity of the fluid layer that is in contact with the sliding plate is equal to the velocity of the plate, while the velocity of the fluid layer that is in contact with the stationary wall is equal to the velocity of that stationary wall, which is of course zero. Thus the velocity of the fluid between the plate and the wall, denoted as small u, varies linearly as a function of y, from a velocity of 0 at the wall, all the way up to a velocity of capital U at the plate. From observation, we find that if the surface area of the plate that is in contact with the liquid is doubled, the force also must double, to achieve the same constant plate velocity u. Hence F is proportional to the surface area of the plate that is in contact with the liquid. We also find that if we double the plate's velocity, capital U, we must also double the force F. Hence F is also proportional to U. Finally, we observe that if the distance capital Y between the moving plate and the stationary wall is halved, the force F must double to maintain the same velocity of the plate. Hence F is inversely proportional to capital Y. Using our observations from the previous slide, that F is directly related to A, F is directly related to U, and F is inversely related to capital Y, we can combine them into one relation. F is related to A times U over capital Y. Since F is affected by the conditions right next to the plate, we replace the term U over capital Y by the rate of change of the velocity in the y direction at the plate-fluid interface, or du by dy. Finally, we introduce the proportionality constant mu, and get the shown equation, where the force F is equal to mu times A times du by dy, where mu is called the absolute viscosity, or the dynamic viscosity, and it has units of Pascal seconds. By dividing the force Fx by the area Ay, we get the shear stress that is acting from the fluid on the plate or the plate on the fluid. Substituting mu times A times du dy for F, we get that the shear stress is equal to mu times du by dy. This last equation is known as Newton's law of viscosity. Shown here is a plot of viscosity mu in Pascal seconds versus temperature in Kelvin for water in vapor form and water in liquid form. Notice that the y-scale of the graph is logarithmic in order to better show the trend in the viscosity versus temperature of both liquid water and water vapor. Despite the large difference between the viscosities of these two water phases, to switch to a linear y-axis scale, you can click on the button under the graph. This plot will be used in the explanation of the origins of viscosity. Viscosity originates from two main physical phenomena: molecular cohesion, which dominates in liquids, and molecular momentum interchange, which dominates in gases. The molecular cohesion effect causes molecules that are closely packed, such as the molecules of a liquid, to tend to stick together. Molecular cohesion is the dominant cause of viscosity in liquids. It does not, however, play an important role in the viscosity of gases, since the fluid molecules are much farther apart in gases. Since high temperature tends to weaken molecular cohesion and to increase intermolecular distances, liquid viscosity tends to decrease with temperature. As can be seen on the shown figure of the viscosity of liquid water versus temperature. In gases, on the other hand, viscosity is mainly due to the interchange of momentum between the gas molecules, whereby the slower moving gaseous molecules interact with, and slow down the faster moving gaseous molecules. The mixing of gas molecules from different velocity layers within the fluid tends to promote the interchange of momentum between molecules from these layers of different velocities. Since temperature increases this random mixing motion within fluids, gaseous viscosity tends to increase with temperature, as can be seen from the shown figure for the viscosity of water vapor versus temperature. Notice that both liquid water and water vapor have the same viscosity at the critical temperature of water, which is 647.14 degrees Kelvin. This is the temperature at which liquid water and water vapor become indistinguishable. In SI units, viscosity is usually expressed in units of Pascal seconds, which is equivalent to kilograms per meter second. Another common viscosity unit is poise, which is equivalent to grams per centimeter second. The conversion relationship between poise and Pascal seconds is that 1 Pascal second is equal to 10 poise. The table shown here gives the viscosity values of some common fluids. A fluid with a zero absolute viscosity is called an inviscid fluid, or a superfluid. These fluids can be obtained by cooling some substances such as helium to a temperature close to absolute zero. In fluid dynamics, an inviscid fluid assumption is usually employed to simplify the analysis of some flow problems. In laminar pipe flow, an inviscid fluid has a flat velocity profile that is called a plug flow, where the velocity is the same at any cross-section of the pipe that is perpendicular to the flow direction. A viscous fluid, on the other hand, is any fluid that has a non-zero absolute viscosity value. In laminar pipe flow, a viscous fluid has a parabolic velocity profile. This is due to the fact that at the pipe's wall, the velocity is zero, due to the no-slip boundary condition at the wall that we discussed earlier. The velocity is maximum at the center of the pipe, which is the point that is furthest away from the pipe's walls. The velocities of the fluid layers that are between the pipe's wall and the pipe's center have intermediate velocity values.